All right, so today we're going to just go over some examples of parametric equation problems. So there are two problems here. We're going to do these together, and then you'll have time to work on these down here. So sketch the motion of a particle whose position at time t is x equals f of t, right? And that's graphed right here. So it's x. So the position of the particle as an x coordinate over time is represented by this graph here. So t is the x-axis and x is the y-axis. And then y equals f of t, so y as a function of time. So just the vertical position, the y-coordinate over time, and that's graphed here. Where graphs f and g are shown below. Indicate the direction of motion for the particle. All right, so here we're going to graph just x and y. So here's our y-axis, and here's our x-axis. And as t increases, we're going to show arrows to show the motion of the particle. All right, so if we make a little table here, we got t, x, and y. So when t is 0, so at the starting point, the x position is 0, and the y position is 0 as well. So on this graph here, we're just going to graph the x and y coordinates, 0, 0. But when we graph our next point, we're going to show an arrow going in the direction from the point where t is equal to 0 to the point where t is equal to 1. All right, so when t is equal to 1, so now we look on both graphs where t is equal to 1, we see that x is equal to 2 and y is equal to 0. So now we have the point 2, 0. So this is at t equals 0. This is at t equals 1. So I'm going to connect the dots here and show an arrow pointing from 0 to 1. So that's the motion of the particle after 1 second. All right, and then from 1 second to 2 seconds, we now got to graph the point where t is equal to 2. So we got t is equal to 2. All right, x is equal to 2. Y is equal to 1. So now I have the point, the x and y coordinate 2, 1. So that'll be right here. So I'll connect these dots and put an arrow. All right. Now we keep going. So t is equal to 3. All right, look at this graph. We know that, all right, x is 0 when t is equal to 3, and y is 1. So 0, 1 would be right here. So connect those dots, and then show the arrow pointing from where t is equal to 2 to where t is equal to 3. And then for t equals 4, we got x is 0 and y is 0. So we're right back to where we started. And that's how we do it. So you don't need to make that table middle step, but I just kind of did it to help explain what was happening. But basically, we're just eliminating the parameter. We're using these two graphs to find the different points at different values of time. And then we're just graphing the x and y points, but using the arrows to show where t is increasing. So this is t equals 0 to 1, 1 to 2, 2 to 3, 3 to 4. Now, maybe moving in more of a circular path, it may not like an elliptical path. It may not be moving like in straight lines like that, but I'm fine if you sketch it like that. All right. So I'll leave this blank for now, and then at the end, you can go back and try this, and then we can go over it later. But I want you to try this on your own. But if we have no questions on the top part, we could go on to number 2. Questions? All right. So let's flip it over. All right, and I may need to use the calculator here. Let's make sure it's ready. Yes, sir. All right, so let's read this. So a large coordinate grid is mapped out on a gym floor for the robotics competition. The robot named Kismet is at the point 2, 10 when Jake started watching it. After 5 seconds, it crossed the lattice point 8, 7. After another 5 seconds, it crossed the lattice point 14, 4. So draw a picture of what's happening with Kismet. What assumptions are you making? All right, so let's start back from the top. We got a coordinate grid here that represents the gym floor. So if you have like a space, like a plane, you can assign an X and Y axis so that you can describe the position. So we'll assume that this is at like 0, 0, and that's our X axis, and that's our Y axis. So it's at the point 2, 0, and Jake started watching it. So let's plot that point. Over 2, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's right here. And we'll say t is equal to 0, just so we remember that's where it's starting. So after 5 seconds, it crossed the lattice point 8, 7. So that just means like lattice point, that's like the point on the grid. Like a lattice is like when you have things crossing each other. So 8, 7 would be here at 1, 2, 3, 4, 5, 6, 7, 8, up 1, 2, 3, 4, 5, 6, 7. All right, so that's 8, 7, and that's at t equals 5. All right, so 8, 7, 2, and 10. And I'm going to connect these 2 points with a straight line with an arrow showing where t is increasing. All right, after another 5 seconds, it crossed the lattice point 14, 4. So 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4. So 14, 4. So this is another 5 seconds, so that'd be at t equals 10. And then, there we go. Now, I'm not quite sure if this is one straight line, and one way we could tell is to see if the slope between these 2 points is the same as the slope between these 2 points. So if we check, we go down 3 over 6, down 3 over 6. So this is just one straight line. And don't assume that unless the slope stays the same, because it could be like down 3 over 7, and it might look like a straight line. Yes? Did I count wrong? Oh, good. All right, nice. Sorry, I think I know. All right, great. So now this is at 14, 4. So I just marked that off on my grid so I could easily find those points. All right, so draw a picture of what's happening. What assumptions are you making? All right, well, any ideas what assumptions we're making? So it says that Jake noticed it was here at t equals 0, here at t equals 5, and here at t equals 10. So that we can't assume. We're just like, those points are law. Like we have to do those points. Yeah. Moving at a constant rate, right? It could have went backwards like slowly and then sped up right to there. Right, so we're assuming it's moving at a constant rate. That's true? Yeah. Moving in a straight line, yeah. It was here, then here, and then here. So like if you open your eyes and you see it there, and then close your eyes, and then open your eyes and see it there, and then close your eyes and open your eyes and see it there, sure, it could have just moved in a straight line, but it could have also like went this way and then that way. All right. And that's what math in the real world is, because the real world is complicated, it's messy, but sometimes to get it something to describe it as like a math equation, or you have to make assumptions. And sometimes the assumptions are wrong, and then you go back and you fix it. But for any mathematical model, assumptions have to be made. So I'm not saying it's right, but in order to help us based on what we know, it makes the most sense just assume it's in a straight line. All right, awesome. All right, and it's moving in this direction, but like I said, like it could have moved away and then looped back around. All right, so we're making an assumption it's moving in one straight line. All right, so moving, we'll just say moving in a line at a constant rate. All right, so where is it after 17 seconds? So we could estimate that by just like keep plotting points. Like, all right, after 15 seconds, it'd be around here. And then after 20 seconds, it would be over here. So like it'd be, somewhere down here after 17 seconds. All right, but that's a little sloppy. So if we're using this as an assumption, we could write a set of parametric equations that model the position of this robot Kismet at any point in time, and then plug in t equals 17 to find the position. So to do that, all right, the x position is equal to the starting x coordinate, which is 2, plus how far it travels in a certain amount divided by that amount of time. So from t equals 0 to t equals 5, in the x direction, it moves 1, 2, 3, 4, 5, 6 every 5 seconds. And then we multiply that by time. So it's moving 6 units to the right every 5 seconds, according to these 3 points. So we're going to assume it's going to keep doing that. And then in the y direction, it starts at 10 on the y coordinate, but it goes down 3 every 5 seconds. So we'll actually go plus -3 over 5 times t. So to figure out like where this is after 17 seconds, well, that is t is 17. So we're going to plug 17 into each of these and get an answer. So it would be at 2 plus 6/5 times 17, and then 10 plus -3/5 times 17. And now we'll just type that into our calculator. And sorry, you can't see, it's kind of dark. If that ever happens, I can turn this light on. Motel 6, we'll leave the light on for you. That's what our class is brought to you by today, our sponsor, Motel 6. We'll leave the light on for you. All right, so 2 plus 6/5 times 17 gives us an x coordinate of 112 over 5, which you can convert to a decimal, and you get 22.4. And the y coordinate would be 10 plus -3 over 5 times 17. All right, and that's -1/5. So as a decimal, that's -0.2. So I'm going to write that down. 22.4 comma -0.2. And you use bless you. Estimating is really important in math, especially in mathematical modeling problems where you're trying to describe something in the real world, because it allows you to see if your answer makes sense. So does this answer make sense? Well, in 10 seconds, it moves from 2 to 14. So it moves over 12. So we'd assume in another 10 seconds, it would move over another 12, which would bring it after t equals 20. That would be 12 plus 14, it'd be at 26. And 17 is in between 10 and 20. So 22.4 makes sense. And also, if you look, like after 10 seconds, it moves down from 10 to 4, so it goes down 6. So after another 10 seconds, it'd move down 6 again and be, at -2. So that makes sense. Now, when will it cross the x-axis? So any ideas how we can use these parametric equations here to figure out the time in which it crosses the x-axis? Yeah, Brian? Beautiful. 0 in for y, because the x-axis is the line where all the y coordinates are 0. And the y-axis is the line where all the x coordinates are 0. All right. So that's no one from this class talking, right? All right, I'm losing my mind. All right. I was like, okay. So yeah, so y of t equals 10 minus, and I wasn't saying that like, who's talking? Like I thought someone was asking me a question and I was hearing voices in my head. All right, so you were gonna set that equal to 0. So 10 plus -3/5 t equals 0, and then we could solve that. We could subtract -10 on both sides, and then do -10 divided by -3/5, which would be positive. So that's the same thing. So the negatives will cancel out. And that's the same thing as multiplying by the reciprocal. So that's 50 over 3, which 48 over 3 would be 16. So that'd be like 16 2/3. It's like 16.66 repeated. All right, so when will it cross? And that makes sense too, because at 17 seconds, it just got below the x-axis. So it should be right before 17 seconds, it crossed the x-axis. All right, now, if Kismet has been traveling in this manner for a while, meaning maybe it didn't start here, it started over here, and we just started counting here. So it didn't have to start moving there, but we're gonna say that's t equals 0. That's when we started, that's when Jake started watching it. All right, how can we figure out what time it crossed the y-axis? Well, we can use the same logic that Brian just did, but now since it's the y-axis, plug in 0 for x. So to see when it would cross the y-axis, we're gonna plug in 0 for x, but also keep in mind that we could definitely get a negative answer, and we should get a negative answer because when t is 0, it's to the right of the y-axis, and as t increases, it moves more to the right. So if we're moving to the left, t is going to decrease from 0, which means it has to be negative. So, and I'll show you how to interpret that, but we'll subtract 2 on both sides, and then t is equal to -2 over 6/5, which would equal -2 times 5/6. And that's going to be -10 over 6, which is -5/3. Which means, all right, that's like -1.66 seconds. That would mean it crossed the y-axis 1.6 seconds before Jake started watching. So the thing doesn't have to start moving at t equals 0. That's what we chose to be like t equals 0. All right, and then what are the parametric equations for the robot's path? Well, we did that already, Susan. That's baseball, Susan. Right there. Boom. Okay. So I'm going to pause the video.